Lecture 2 is a continuation of the topic of vector analysis. You may recall that we were discussing vector algebra and in particular the multiplication operation for vectors. We had discussed scalar product and the dot or scalar we had discussed the product of a scalar quantity with a vector as well as the scalar product of two vector quantities, also called the dot product. In this lecture, we will begin with the vector product of two vectors, also called the cross product. Let there be two vectors quantities, vector u and vector v. So, we define the cross product of u and v, namely u crossed with v as the product of the magnitude of u, magnitude of v and sine of the angle between u and v. Again the smaller angle is considered. So, sine theta. Now, since this product gives me a vector quantity, so the question naturally is asked, which is the direction of this quantity. The direction is obtained as follows: vector u and v, a unique plane can be passed through vector u and v as shown in this figure over here. This white is the plane containing both vector u and v, and the normal vector to this plane, that is vector n. This is a unit vector which is simultaneously normal to vector u and vector v. Now, the positive direction of n is obtained by the right hand screw system, as we did for the coordinate axis, you may recall. So, if I rotate from the screw in the direction from u to v, that is in the anticlockwise direction, then the right handed screw will move in the positive direction of n. So, this is how you can obtain the positive sense of the unit vector n. Now, there are certain properties associated with this vector product or cross product, namely vector u crossed with vector v is no longer equal to vector v crossed with vector u, as we saw in the case of dot product. No, in this case, it is a negative quantity. So, u crossed with v is equal to minus of v crossed with u, that is, it is a non-commutative law. This is easy to understand because by the screw right hand screw system, u crossed with v. So, we rotate the screw from u to v. When you consider v crossed with u, you rotate the screw from v to u. So, opposite direction. So, hence it is a negative quantity. Well, the distributive law is still valid. U crossed with v plus w, that is the sum of v and w, is equal to the sum of the product of u crossed with v and u crossed with w. That is, you first multiply individually and then add, or you first add v and w and then multiply u with it. So, this is the distributive law. There are some interesting special cases of the cross product, namely when u is parallel to v, two vectors are parallel and their cross product is taken. What does it imply? When there are two parallel vectors, the angle between the two, that is angle theta, will be equal to 0 and sine of 0 is also 0. So, obviously, u crossed v is equal to 0. Now, we take the cross products of individual unit vectors. Suppose I consider two unit vectors I and j, that is along x axis and y axis. So, you can easily see, let us say this is the x axis, this is y axis and this is the z axis. So, u crossed with j, I crossed with j will give me the k vector, j crossed with k will give me the I vector, k crossed with I will give me the j vector. So, I j k. So, I crossed with j will give me k, j crossed with k will give me I, etc. If I reverse the operation, that is j crossed with I, this will give me the negative quantity minus k vector, and so on and so forth. So, you can see in this operation in a very simple way. I crossed with j is giving me k, j crossed with k gives me I, k crossed with I gives me j, and if I, so this is going in the clockwise direction. If I go in the opposite direction, that is I crossed with k, that will give me minus j, j crossed with I will give me minus k, etc. So, depending upon the order of vector multiplication, the unit vector is obtained. Let us see the cross product in the component form. The two vectors are u and v, whose components are ux, uy, uz, and vx, vy, vz respectively. So, I multiply these two vectors. Now, let me take the first term ux I unit vector. When I multiply with I unit vector with I unit vector, we have seen the cross product is 0. I with j will give me k, I with k will give me minus j. So, in this way, if next I take this second term, then third term, and if you collect all these terms, you will get u crossed with v is equal to u y v z minus u z v y I into unit vector I. Similarly, u z v x minus v x u x v z multiplied by the unit vector j, etc. And this thing, this whole expression can be very easily checked to be equivalent to the determinant of this matrix. And which is this matrix? The first row is consisting of the unit vectors I, j, k. Second row is the components of the first unit vector, first vector, and the third is the consists of the components of the second vector v. Okay. So, if I carry out the determinant operation, that is for finding out the determinant of this 3 by 3 matrix, the expression will be exactly as given over here. Perhaps this expression is easier to remember than this. So, you can easily check yourself. Let us now look at the geometrical representation of the operation of cross product. Here is vector u and this is vector v. So, we have already seen it is the magnitude of u and times the magnitude of v times the sine of the angle between the two vectors. So, here is sine theta, angle theta. So, you can see that this magnitude times the sine of this angle. So, v times sine of this angle is this vertical altitude. So, this gives me the area of the parallelogram OACB, which is equal to the base times the altitude. So, the magnitude of u cross v is equal to the area of the parallelogram whose two adjacent sides are in the direction of u and v, and the magnitudes are proportional to their magnitude. Okay. And what is the direction of this? The direction of this product, cross product, is simply the unit vector perpendicular to the plane of the parallelogram, and again the sense is determined by the right hand screw system. Final algebraic operation for vectors is the division of vectors. Well, a vector can be divided by a scalar only. In this case, the magnitude of the vector gets divided by the scalar quantity, but the direction of this quotient remains unchanged. So, all you do is you divide the magnitude and do not disturb the direction of the vector, but the division of a vector by a vector quantity is not defined. There is another type of product which is sometimes encountered in mechanics, namely the triple scalar product. Well, it consists of first a vector product between two vectors A and B, for example. So, A crossed with B, and this product is then dotted with vector C. So, A crossed with B dotted with C is equivalent to C dotted with A cross B. This is due to the commutative law of dot product, and the magnitude wise either this or this both are equal to the magnitude of A times magnitude of B times sin theta. So, this is the cross product of A and B, and the direction of this product is the unit normal n dotted with the this should be dotted with the magnitude the vector C. Okay. So, this is the final expression for this triple scalar product, and in the determinant form you can easily check that this will be equivalent to determinant of the matrix consisting of the three vectors A, B, C written A x. So, the first row is A x, A y, A z, that is the three components of vector A. Second row is three components of vector B, and the third row is the three components of vector C. Well, as before, we will try to understand this triple scalar product graphically also. Here are three vectors A, B and C. First, you will complete this parallelogram, and then you will complete this parallelepiped like this. So, from C so, it makes a parallelepiped. So, the triple scalar product will be simply the volume of this parallelepiped. You compute the volume of this parallelepiped having three adjacent edges as A, B, C, and you will find that the magnitude of this volume will be exactly equal to the magnitude of the triple scalar product. There is another geometrical interpretation for the scalar product, namely it represents the projection of a vector on a line. For example, here is vector v, an arbitrarily given vector, and an arbitrary direction of the unit direction in this is represented by unit vector n. Now, if you draw the projection from the tip and the tail of this vector, let it be C d. So, this length C d is equal to v dotted with unit vector n. N is the let us say it should be unit vector n. Okay. So, this is equal to the magnitude of v times the cosine of the angle between the vector v and the n unit vector. So, this angle I have drawn. So, this line is parallel to the unit vector n. Okay. So, as special case, we can take the projection of vector v on the unit vector along x axis, that is I vector, which will give me the component of v in the x direction bx. Similarly, if I take the projection of v on y axis, that will be v dotted with j. So, this will give me v y, and similarly v z. The application of this concept is in the determination of work done by force. You must have learnt in your earlier mechanics courses, perhaps in physics or elsewhere, that is the work done by force in moving a particle from position 1 to position 2, that is along a vector r, is equal to magnitude of force times the distance times the angle between the force and the direction of movement, that is magnitude f times magnitude r times cosine of angle theta. So, the angle theta is the smaller angle between the two lines, this is angle theta. Okay. So, this scalar product as a projection of line is interpreted as a physical quantity, namely the work done. Now, another useful concept associated with vectors is the direction cosines of a vector quantity. The components of vector v as are obtained as projections on the coordinate axis. For example, I have just shown you that Vx is equal to the projection of V on the unit vector I, that is V times cosine alpha. So, the alpha is the angle which vector V makes with the x axis. What you do is that you pass a unique plane with vector V and x. Okay. You can always draw a single plane passing through two straight lines and you measure the angle alpha in that plane. Similarly, when you come to angle cosine beta, well then this is cosine of this is the angle between vector v and the y axis, and this is the angle between vector v and the z axis. So, each time you consider the unique plane containing the vector and the corresponding axis. So, angle alpha is the angle between x axis and v, angle beta is angle between y axis and v, and angle z angle gamma is the angle between v and z axis. Okay. So, we can show that the sum of the squares of the cosines, cosine square alpha plus cosine square beta plus cosine square gamma is Vx square plus Vy square plus Vz square as given over here, divided by the magnitude of vector V squared, and this is obviously equal to 1 because the numerator and denominator are identical terms. Let us take up an example to fix our ideas about the direction cosines. Suppose there are two forces F1 and F2 which act on the end of a pipe as shown over here. This is a pipe which is fixed at one end, and at the other end there are two forces F1 and F2. F1 is given in magnitude as well as in its orientation. Magnitude is 300 newtons and orientation is obtained by three angles which the force vector F1 makes with x axis, y axis and z axis, namely the angle 45 degrees, 60 degrees and 120 degrees. Okay. We want to find F2, that is its magnitude and direction cosine, such that the sum of the vectors F1 and F2 is along the y axis. So, such that the sum or resultant is along the positive y axis and has a magnitude of 800 Newton. So, both the magnitude and direction are given. Well, to solve this problem, let us first find out the unit vector along the direction along the force F1. Well, cosine of alpha is cosine 45 degrees. So, it will be cosine 45 degrees unit vector I, cosine 60 degree unit vector j, cosine 120 degree unit vector k. So, Well, you know the cosine of 45 degrees is 1 by root 2. So, I unit vector root 2 divided by root 2 plus j unit vector divided by root 2, and cosine of 120 degrees is equal to negative of root. Yeah. This is 1 by 2. So, this will be minus, please sorry for mistake. So, it is 1 by 2. So, this is, there is no under root sign over here. So, you can easily see that this is equal, and this will be also equal to, there is a mistake over here also. So, you can find out F1 is equal to 212.1 unit vector I plus 150, that is 300 by 2 unit vector j, 150 unit vector k. F2, since we do not know its magnitude, we know only its in the component form will be F2x I plus F2y j plus F2z k. So, these are the three components. We know that the sum of these two vectors F1 plus F2 is equal to the resultant force, and this is given as 800 in the positive y direction, that is unit vector j. So, we get the vector equation 212.1 plus F2x unit vector I 150 plus F2y unit vector j minus 150 plus F2z unit vector k equal to 800 j. All right. Now, this vector equation is equivalent to three scalar equations, that is compare the I components with I components, which is 0 on this side, j components with j components. So, we will have the and similarly the this will be equal to the k components with k components. So, you can say easily write this as 800 j plus 0 I unit vector plus 0 k unit vector. Okay. So, first we will compare the I components, that is 212.1 plus F2x is equal to 0. So, this will give me F2x is equal to minus 212.1 newtons. Similarly, second will be 800 j, 800 is equal to 150 plus F2y. So, F2y will be equal to 800 minus 150. So, it is 650 newtons, and finally, F2z minus 150 is equal to 0. So, F2z is equal to 150 newtons, and if I find out their magnitude of force F2, which is equal to the x component square plus y component square plus z component square whole under root. So, this will be 212.1 square plus 650 square plus 150 square. This will give me 700 newtons, and cosine of, now we find the individual direction cosines. Individual direction cosines are cosine alpha 2 which is equal to F2x divided by the magnitude of f, which is equal to minus 212.1 divided by 700, which is obviously equal to minus 0.307, and similarly for cosine beta, cosine gamma. So, we will have F2 as the magnitude times cosine alpha I plus cosine beta j plus cosine gamma k. So, 700 into minus 0.307 I, 0.928 J, 0.214 K. So, this is the final expression for the force F2. We will take up another example. A heavy box weighing 25 kilonewtons is to be lifted by two overhead cranes with cables inclined. So, in a factory situation, you have a heavy box which is being picked up by two overhead cranes. So, the cable of one is inclined at 30 degrees to the vertical and the second cable is inclined at 45 degrees to the vertical. So, find tension in each cable during lifting operation. Due to, and second part of the problem is that due to safety concerns, the tension T2 in the second cable is to be minimized, otherwise it may break and there can be an accident. So, find the angle of inclination of this cable for this purpose. So, here is a box, here is a load acting downward, the weight, that is 25,000 newtons or 25 kilonewtons, and these are the two forces. So, for just lifting the box, just moving it up, the sum of these two vectors should be equal to exactly 25 kilonewton in this vertical direction. Well, we can easily look at this problem in a graphical manner, and we will use the triangle law of addition of two vectors. There is a vector T1 along the direction of the first cable, that is at 30 degrees to the vertical, and the second tension is at 45 degrees to the vertical, and both of them have to be equal to 25 kilonewton. So, if we draw a triangle, first of all we draw the vertical line of representing 25 kilonewton, maybe let us say 1 centimeter equal to 5 kilonewton. So, this is a 5 centimeter line vertical, and along T1 so from A we draw a line parallel to T1, and from B a line parallel to T2, wherever they intersect, that is the point C, the apex of this triangle, and you can easily see this angle at C will be equal to 105 degrees. And now you use the well known sine law of triangles. So, AB divided by, this is AB divided by the opposite angle, that is 105 degrees. So, AB divided by sine of 105 degrees is equal to T1 divided by the opposite sine of the opposite angle, sine 45 degree, T2 equal to T2 divided by the opposite sine of the opposite angles, that is sine 30 degree. So, we can easily see that from the first equation, because AB is 25 kilonewton, that is given to us. So, T1 is equal to 25 into sine of 105 degrees divided by sine of 45 degrees, which is 18.31 kilonewton. T2 is equal to 25 into sine of 105 degrees divided by sine of 30 degrees, that is 12.94 kilonewtons. So, both these cable tensions are easily obtained by simple sine law of triangles and using the triangle law of addition of vectors. To find the minimum value of T2, it is very easily understood graphically. Again we have drawn the 25 kilonewton line, okay, and the direction of T1 is known to me. Of course, its magnitude is not known. Now, from point B, I will draw a line to represent T2, which will be the shortest distance between B and C, okay. And let us say from B, this can be one line. If I extend the line of AC, this can be another line, this can be another line, this can, so there can be several lines, but which gives me the shortest distance? Naturally the line which is normal to line AC. So, I will draw a perpendicular to line AC. So, wherever it meets this direction of T1, that will define my point C. So, once I have got 30 degrees and 90 degrees over here, so this angle will be automatically equal to 60 degrees. And again you use sine law of triangles, you can find out that T2 will be equal to 12.5 kilonewtons and its direction will be 60 degrees to the vertical. So, this minimum tension in cable 2 is obtained when the inclination is 60 degrees. If we do the same problem analytically, well, if I go back to the, you can easily see tension T1, let us say this is my x axis and this is my y axis. In all problems of this kind, first you should fix your axis. So, this is my unit vector I, this is unit vector j. So, if I resolve the components of T1, so naturally it will be T1 cosine of 60 degrees in unit vector I plus T1 cosine of 30 degrees unit vector j. But for T2, the I component is in the negative x direction, j component is still vertically up. So, it will be T2 cosine of 45 minus I unit vector plus T2 cosine of 45 degree plus j unit vector. So, accordingly we will have T1 is equal to vector T1 is equal to the magnitude of T1, that is simply T1 divided by 2 I unit vector I, that is sine of 30 degrees, and this will be T1 into sine of 60 degrees, that is root 3 by 2 j. For T2 it will be, as I said, in the negative x direction. So, minus T2 sine 45 degrees minus T2 cosine 45 degrees. So, these are the two component representations of the tensions T1 and T2. So, sum of these two vectors T1 vector plus T2 vector is 25 j kilonewtons. Now, again this vector equation is equivalent to two scalar equations, and you can see that it will be T1 over 2 minus T2 over root 2 is equal to 0. So, T1 is equal to root 2 times T2. From the second equation you will find that T1 into root 3 by 2 plus T2 divided by root 2 is equal to 25. So, solving these two equations for two unknowns, simple linear algebraic equations, you will find T1 is equal to 18.5 kilonewtons, T2 is equal to 12.94 kilonewtons. So, same results we had obtained graphically, that is obvious. But to find the minimum tension T2, the procedure is slightly more involved. Suppose when the cable T2 is inclined at angle alpha to the vertical, then the minimum is obtained. Then the vector T2 can be represented as again minus T2 sine alpha, because it is in negative x direction, plus T2 cosine alpha in the positive j direction, and we will again have a one vector equation equivalent to two scalar equations. So, the equations will be T1 equal to T2 sine alpha and T1 root 3 by 2 plus T2 cosine alpha is equal to 25. And from these two, let us eliminate T1, which will give me this simple equation. Now, to find out minimum value of T2, naturally this term should be maximum, because it has to divide 25. So, when the denominator is maximum, the term is equal to T2 will be minimum. So, the problem reduces to maximizing this expression cosine alpha plus root 3 sine alpha, and this can be done by simple calculus, that is the derivative of this expression should be equal to 0, and when I take the derivative of this expression I get tan alpha is equal to root 3, and hence alpha is equal to 60 degrees. So, again we come to the same conclusion that when the second cable is inclined at 60 degrees to the vertical, the tension in that cable is minimized. And okay. Now, we come to some useful vector quantities which will be encountered time and again during the this course. These quantities are first of all the position vector. Suppose there is a vector p and there is a point p in the 3-dimensional Euclidean space whose coordinates are x, y, z. Okay. Then the position of this point p with respect to the origin of the coordinate system is defined like this. You join this O with point p, then the vector both in magnitude and direction is called the position vector. So, suppose I take the projections of vector r on x axis, y axis and z axis, and we have already seen how to take the projections graphically. That is, you project this vector r on z axis and one on component on the xy plane. So, this will be the projection along z axis and the red line will be the projection in the xy plane, and this projection is further projected on x axis and then on y axis. So, this will give me quantity x, quantity y, this is x projection, y projection and this is your z projection, and r is written as x I, y j, z k. So, x times unit vector along x axis, that is I, y times unit vector j, z times unit vector k. Suppose there are 2 points in this space, point A and B. So, the unit vector of A is R A vector, unit vector of B is the R B vector. Okay. Then the vector joining A to B, which I am writing as R A B vector, is equal to the vector R B unit the position vector R B minus the position vector R A. Okay. So, in other words, the sum of R A plus R A B is equal to R B vector. Okay. Green vector plus black vector gives me the red vector, and conversely the difference between these two R A B is equal to R B minus R A. Let us now define a very important quantity associated with the force, because this represents the turning action of the force. Force has two actions, one is push and pull and the other is the turning action. Now, suppose there is a force vector F. The line of action of this force is the line AB, and the moment of this force about the given point O is defined like this. Moment m is equal to the cross product of r and f. Okay. Now, what is vector r? Vector r can be any point on the line of action of force F, whether I take this as a point or this as point or this as point. So, you can see whether this as the point or this as the point. So, these are the different unit vectors. Sorry for, let me draw these again. Let us say it can be this vector or this vector or any other vector. Okay. So, whether I define this as vector r or vector r dash, so it is r cross f or r dash crossed with f. And you may be asking, will it give me the same quantity if I multiply it with r or r dash? Yes, because we can easily see that r minus r dash vector will be a vector along the point joining these two tips. So, it will be parallel to f. So, r vector minus r dash vector will be parallel to vector f, and the cross product of two parallel vectors we have already seen is equal to 0. And what are the now this is the expression for your moment. What are its units? Well, force is in newtons and the units of the position vector r are simply the length of the vector. So, this is Newton meters. So, the units of the moment are Newton times meter, it is a derived unit. And what is the direction of m? Just as we fix the direction of u cross v, that is when we go from vector u to v and move the right handed screw in accordingly, the direction of movement of the screw gives me the direction. So, r cross f means if I take the unit vector r and unit vector f, so you can easily see the movement of the screw will be into the plane of the screen. So, you will determine the direction of the moment according to the right hand screw system. Okay. So, we have seen both the direction, magnitude and the sense of the moment vector. Suppose there are two parallel forces, force F and force minus F. Okay. That is their directions are same, their magnitudes are same, but the sense is opposite to each other. So, one is force F, the other is force minus F. Suppose I choose an arbitrary point O in this space and I find out the moment of force F about O and then the force of the moment of force minus F about O. So, and add the two moments. So, it will be r crossed with F plus r dash crossed with minus F dash and minus F. So, it is obviously r minus r dash vector crossed with F, and the vector, this difference vector you can easily see is the vector joining A and B to A. So, this is vector D. Okay. So, the moment of a couple is defined as the vector joining these two points arbitrarily taken on the line of action of the F and minus F forces crossed with the magnitude of that force. Now, I make a very useful statement that this moment obtained in such a manner is a free vector, that is, it is independent of the choice of O. First of all, we have seen the independence of the choice of A and B. I can choose B over here, A over here, or B over here, A over here. All of them will give me the same magnitude of same value of the moment of the couple. And second independence or freedom is the choice of point O. Suppose I choose this as O dash. Okay. Now, let us choose a different color. Now, from O dash again I choose point A and B, same points, because the choice is arbitrary. So, why not choose the same points B on the force minus F vector and A on. So, the corresponding vectors will be, let us say, I will call this as vector S dash, and then I choose join with A. So, this I will call vector S. Okay. Now, go through the same calculation. So, it will be S crossed with F minus S dash plus S dash crossed with minus F dash F vector. So, again the difference vector between the S and S dash will be again D. Okay. So, I will get the same value D crossed with F. So, moment of a couple is a very interesting quantity, that is, it is independent of the point about which the moments are taken, O and O dash, and for calculating this I can choose any 2 points on these 2 lines of action of the forces. So, hence it is a free vector. Let me consider one example of how to take the moment of force. For example, there is a force of 60 newtons which is passing through the point C, which is whose Cartesian coordinates are 3, 4, 0, and it is acting on the end of a rod AB. The end point, one point of the rod is at the origin, the other is point B, whose coordinates are 1, 3, 2. So, the line joining the point C to B is the line of action of force F, and its magnitude is 60 newtons. Determine the moment created by the force about point A. Okay. First of all, we will represent the force, magnitude is 60 times the unit vector along the line of action, that is E is the unit vector which is along line CB. Well, the line joining C to B is the vector RCB divided by its magnitude will give me obviously the unit vector, and the vector RCB will be the difference between the corresponding coordinates 1 minus 3. You can easily see if I go to the previous slide, 1 minus 3, that will be the x coordinate, 3 minus 4 y coordinate, 2 minus 0, that will be the z coordinate. So, accordingly I have the vector RCB given above and divided by its magnitude, that is the sum of the under root of the sum of the squares. So, minus 2 square plus minus 1 square plus 2 square. So, this gives me the unit vector. You can check that its magnitude will come out to be 1. So, the force F will be equal to minus 40 I unit vector minus 20 j unit vector plus 40 k unit vector. Now, the moment m is equal to the distance of the origin, because we are taking the moments about the point A. Let me go back to we are finding out the moments about point A. So, one point is this, the second point is, you can choose any point along the line of action. Why not choose point B, or why, because this is already known, or we can choose point C. You will see that both the choices will give me the same final result. So, I have chosen point B, and accordingly RB, the position vector of point B crossed with F, and this will also be, as I said, RC crossed with F. So, representing the cross product as the determinant of a 3 by 3 matrix I j k, magnitude of RB, the components of RB 1, 3, 2, components of F minus 40 minus 20 plus 40, and if I carry out this multiple evaluation of the determinant, it will come out to be 160 I minus 120 j plus 100 k. So, we close our vector analysis. At this point, we have seen that there are many operations involved in vector analysis, and it can represent very useful quantities like force, like moment, position, and similarly we can represent velocity, etc. In our next lecture, we will be concentrating on the application of vector analysis to forces, namely the equilibrium concepts, free body concepts, etc. Thank you very much.